Let us start discussing a special kind of games which is known as the matrix games. The technical name will be a two-player zero-sum games, which we'll discuss later when we explain these games. We will also discuss why it is called matrix games. So why are we discussing these games? Because this class gives you certain nice properties about the stability and security notions. We have already discussed about the pure strategy Nash equilibrium and the min-max strategies, which gives the stability notion and the security notion respectively. So let's formally define this matrix games. So as we already know that to define a game in the normal form, we need three information. One is the set of players, which is denoted by n. The set and the strategy set of those players and their utilities. So in this special case, there are only two players. Therefore, the set n is only 1 and 2. And the utilities for player 1 and 2, if they are summed, they will be identically equal to 0. So this notation here means that this is if you look at the function utility of 1 plus utility of 2, then it will be an identically equal to 0 function. And that is the name why it is called a zero-sum game. So if you take the sum of the utilities of player 1 and 2, it will always be equal to 0. So let's jump into the examples. So penalty shootout game, which we looked at last time, I have reduced some of these strategies. Instead of the center strategy, now the players, both the shooter and the goalkeeper, has only two strategies, either to shoot on the left or the right. Goalkeeper can only dive on the left or right. And quite naturally, when the shooter shoots to the left and goalkeeper jumps to the left, then shooter gets a -1 utility and goalkeeper gets a +1 utility. Now this is a two-person zero-sum game. Two-person because there are only two players, the shooter and the goalkeeper, and zero-sum is because at every outcome of this game, if you look at the sum of the utilities, they are summing to 0. Let us also look at a little larger but an arbitrary game. So this has three strategies for player 1 and player 2, and you look at the numbers at every outcome of this game, every strategy profile of this game, the sum of the utilities is equal to 0. Now why it is called matrix game? So that is an important thing. So you can notice that it is possible to represent the game with just one matrix, let's say U. Because the utility of the second player is always going to be the negative of player 1, then we can just denote the matrix with the numbers or the utilities of player 1, and that will be sufficient to describe this game. And that's the reason why this game is called a matrix game. Now in this situation, let's consider those security criteria. So player 2's max-min strategy. So if you look at the max-min strategies for both these players, player 1 and 2, we have seen that in the previous module, that you take for player 1, you are looking at the minimum over every row, and then you are picking the maximum. That is the max-min strategy. So let's look at the shooter and the goalkeeper game, the penalty shootout game, and for now just consider this part of this diagram. So this is the matrix that represents this matrix game. I'll come to this numbers later. Now if you look at the row minimum, so these numbers are actually representing the row minimum, and the max min will, of course, in this case will be -1. Now if you do the same max min exercise for player 2, what you will get is the min max of this matrix. So in this case, the min max, so you take first take the maximum over the column, and that will give you these numbers for both these columns, and then you take the min, which is going to be 1 in this case, and that min max value, the negative of that, is actually going to give you the max min value for player 2. Now similarly look at the larger game, and you will find that the max min value in this case is 1, and the min max value is also 1. So what does this tell us? Now one important question to ask here is, so what are the PSNs of this game? So let's find that out. I think this is a nice time to pause and think about what are the PSNEs of these two games, and see if you can see a connection between these max-min values and that PSNEs. While you answer that question, let us also introduce a new concept called the saddle point. Note that the saddle point is an idea which is relevant for a matrix. Although we will be calling the saddle point of a game, it essentially means that the game is a matrix game, and we are referring to the matrix of that, the saddle point for that matrix of that game. Now, what does saddle point mean? This is the value that is the maximum for player 1, and it is going to be the minimum for player 2. Okay? So if you want to draw it in a 3 dimensions, so let's say I have these 2 dimensions describing x and y for player 1 and 2, and the saddle point, if I represent these utilities as the 3rd dimension, then saddle point means that you are going to find a maximum over this over the y-axis, and also the minimum over the x-axis. So imagine this is a 3-dimensional plot, and you can think of curves which are 3-dimensional and has a maximum point in one axis, the minima in the other axis. Those kind of points are called the saddle points. And exactly the same thing we are going to ask in the context of matrix games. Now, if I want to rephrase the previous question of finding the PSNE, what we are going to ask is what is the saddle point of these 2 games? You can, if you have answered the previous question of PSNE correctly, you can see already that this game, game 1, the penalty shootout game, does not have a saddle point. Why? So let's consider one point. This is of course the column maxima, but that is not a row minima. In order to become a saddle point, it has to be simultaneously a column maxima and a row minima. While in the second game, if you look at this point, it is a column maxima, but it is also a row minima. So the saddle point in this matrix happens to be this point, m comma r. And now you can actually notice that the game, the penalty shootout game, does not have a pure strategy Nash equilibrium. While for this game, at this point, m comma r is indeed a pure strategy Nash equilibrium. So that intuition is actually being formalized in this theorem, which says that in the matrix game with utility matrix U, S1 star and S2 star is a saddle point if and only if it is a PSNE. Right? So the ideas of saddle point in a matrix game and the PSNE are one and the same. And the proof is extremely simple. All that you will have to start with is the S1 star and S2 star, which is a saddle point. Then it implies and is implied by the fact that you can write this inequality. So you take S1 star and S2 star. This has to be greater than or equal to when you change the first utility. This is a saddle point. Therefore, if you change the utility of player 1, so this thing will be the maximum for player 1. The utility that it will give is the maximum, and this should hold for all S1 in capital S1, while the other player is still holding on to the S2 star. And similarly for player 2, it has to be the minima for player 2, right? So it has to be the row minima. And if you look at this inequality, it has to hold for all S2. And now this immediately tells you that this is a PSNE, because the utility for player 1 is just the utility matrix itself, while for the utility for player 2 is just the negative of it. So if you just invert this inequality, it will also give you that the utility of U2 of S1 star comma S2 star is actually greater than or equal to U2 of S1 star comma S2, and that holds for all S2 in S2, capital S2. So this is the definition of PSNE, and therefore we are done. And notice that this implication is in both directions, so therefore whether you go from left to right or right to left, it's the same thing. Let us also give a name for this max min and min max values. So by V lower bar, we are going to define the max min value of this matrix, and with the V upper bar, we are defining the min max value. Now we are going to ask how they are related to each other, and this lemma is essentially telling that the max min value is actually smaller than, can be at most the min max value. Again, the proof is just by using the definitions carefully. So the first thing that we will do is look at the utility of the matrix entries at S1 comma S2, and this is going to be greater than or equal to the minimum. So this is just by the property of minimum that we have used, and this should hold for all S1 and S2. So we have already fixed this. So this right hand side is no longer a function of S2, but the left hand side is. So this inequality should hold for all S1 and S2. Now you can take a max over both these sides, and the inequality still will should continue to hold. If you are confused about why this max can be taken on both sides, maybe think in this way, that first you take the maxima on the right hand side, and you get this expression. Of course, there will be an argmax, let's say so T1 star, which gives you this max value. Plug that T1 star on the right hand side, and because this inequality is going to be true for every S1 here, so for that T1 star also this inequality will hold. But T1 star is just one strategy. So therefore, if you take the max over all T1s in S1, it must be greater than that. So that T1 star utility at T1 star comma S2 will sit between these two numbers, this max and this max. So therefore the inequality holds. Now once you have taken this max, this will be for all S2, and the last part will be completed just by taking a minimum. So this is so the left hand side is no longer a function of S1 anymore, it is just the function of S2. The right hand side is already a constant, it's neither a function of S1 or S2. So because it is going to be, so this left hand side is greater than or equal to the right hand side, for all values of S2 you can also take the minimum of S2, right? So this will give you the min max value, which is V upper bar, and the right hand side, which is V lower bar, the maximum value.